Welcome to the presentation. In commodity SSDs, NAND flash memory is widely used as non-volatile memory for storing long-time data. But in this presentation, instead of storing data, we will show how we can use a NAND flash memory as a computing engine. So today's presentation will be outlined in these sections. At first, we'll talk about what problem we are solving and with some backgrounds. Then we will show how we can implement the TCFlash, and then we will show our experimental setup and to verify the robustness of this method, what are the results, and finally the contributions and the future work. So bulk bitwise operations are widely used in different type of applications such as homomorphic encryption, genome analysis, and Bloom filters. But one thing common here is that for all the operation, it requires series of bitwise operation in different long operands with a workload size of tens of GBs. In a traditional computer architecture, data required to be moved or accessed throughout the memory hierarchy. And as the workload size increases, the CPU has to go further and the memory bandwidth drops significantly towards the SSDs. So outside storage computing is bottlenecked by the data movement. One common solution of this is in storage computing. So in this case, in storage computing engine is used inside the SSD and it takes the data from the NAND flash memory and just do the computation inside. But this case, it is also bottlenecked by the channel bandwidth of the NAND flash chips. And this is the internal I/O bandwidth inside the chips. What if we can do the computation inside the NAND flash array and just send the results? So in-flash computing can mitigate the data movement bottleneck maximum. So if we start with a little bit of the background from a top-down approach, in a commodity SSD, it has multiple important components. At first, the host interface layer that creates the interface between the SSD and the host computer. Then the flash translation layer that handles all the garbage collection, address translation. And then with the flash controllers in different channels with different flash chips. And in each of the flash chips, there are multiple dies with multiple planes. And each of the planes consists of multiple blocks with multiple pages. If we give a deep look in a 3D NAND flash block only, it looks like a multi-storied building, and each of the layers, the green layers, is the word lines, and the top red layers is the bit lines, and each of these bit lines is connected throughout all the layers using a purple NAND string, and the intersection between the NAND string and the layers is called a single cell. And all the cells connected with gates is considered as a single physical page. Moving forward with a single physical page, in tri-level cell NAND flash memories using the incremental step pulse programming or ISPP scheme, a cell can be programmed in 8 distinct levels. Each of these distinct levels are depending on how much electrons are stored in the charge-up layer. So these 8 distinct levels can be encoded with a 3-bit encoding, gray encoding. And with all the MSB bits, it constructs the MSB page, and with all the LSB bits, it constructs the LSB page. So 3 logical pages is actually one word line is representing 3 logical pages. And if we just read the MSB, CSB, and LSB page, and look at the first cell is showing 101, that means the first cell is in the L3 state. In case of reading, if we give a deeper look in the threshold voltage distribution of all the cells in a 3D NAND flash block, at first we have to apply the reference voltage 3 And then the cell that has less threshold voltage than that are considered as 1. Higher threshold voltage than that will be considered as 0. The same way, to read the CSV page, we have to apply the VREF1 and VREF5. And to read the MSB page, we have to apply 4 more incremental references. One takeaway from this slide is the interpretation of the data actually depends on the application of the reference voltages. If we just change the reference voltages, the data can be interpreted in a different way. Let's start with the TCFlash implementation. So in some prior works such as Flash Cosmos utilizes multi-word line sensing that is not common in typical memory operation, and it uses enhanced SLC programming that requires a significant change in the ISPP scheme. So it requires some test mode commands for implementing this. And in case of parabit, it requires changes in the control sequence, so significantly that also uses the test mode commands. In our scheme, TCFlash is the first demonstration of IFP in-flash processing in commercial off-the-shelf memories. It utilizes the user mode command, and it requires single word line sensing, which is a very common memory read operation. So let's start with a 3-operand OR operation using our scheme. Let's say we have 3 operands A, B, C, and we want to do a bitwise OR operation between these 3 operands. At first, this A, B, C operand should be stored in LSB, CSB, and MSB pages of a single word line. Then we have to shift the reference voltages with specific offset, and then we have to read the MSB page. And then we get the result of the OR operation between these 3 operands. But how we are getting this? Just by changing the offset. So if we give a deeper look in the VT distribution, and if we see the MSB page and the expected result, the only changes with the MSB page and the expected results is the L1 state, L2 state, and the L6 state. And we know that if we change the reference voltages, we can change the interpretation of the data. So let's start with the VREF0. So the cell that has less threshold voltage than VREF0 is considered as 1, and the cells that has higher threshold voltage than VREF0 is considered as 0. But now, if we just shift the VREF0 with some offsets, now all the cells in L1 will be also considered as 1 because they are less than VREF0. In this way, we can represent the MSB read as same as our result. In the same way, if we just shift the VREF2 and the VREF6, we just get the result. But one thing should be noted that we didn't change the results. If we just refresh the offset values, then again we'll get our data, what was stored in the MSB page. One problem of this scheme is there is very less VT margin between the adjacent state, so that creates some errors. But how we can get the 0-bit errors in TCFlash? In this case, we have to do 2-operand operation, and we have to store the operand A in LSB and operand B in CSV and MSB, both of the pages. So in this case, what will happen, the in-between states like L1, L3, L4, and L6 will not be there. So there will be more margin to shift the read references. So then we just have to shift the reference, we'll get the result, and that's it. Till now, we have considered that all the operands should be stored in the pages of a single word line. What if that is not? Let's say the data or the operands are stored in different pages. In that case, we have to use a commodity command, copy back read. We have to move that in the internal data buffer and then just program it in a single word line pages. Then we just have to shift the reference and read it, we'll get the results. Let's start with the experimental setup and the results. In our setup, we have used standalone NAND flash chips, and we have interfaced with the host computers where we have the driver level firmwares as an implementation of the FTL. We have used 4 types of different vendors chip, 15 chips each, from 64 layer to 176 layer from different technologies like floating gate and JerShap. And we just have implemented 3 user mode operation commands like read page, read offset, and soft bit read. If we just look at the experimental results in multi-chip evaluation, what we'll see that for 2 operand AND or an XNOR operation, we are getting 0 raw bit error, and which is very suited for the error sensitive application. But in case of 2 operand NAND, NOR, and XOR, we are getting some errors because of the L0 state is wider and that state is involved with this computation. And then for the low margin between the states, we are getting some errors for 3 operand operations for AND, OR, and XOR operation. So these operations will be well suited for the error tolerant application. But what is the root cause of these raw bit errors? If we just do the 3 operand operation, the margin between 2 states is very low, and for getting the 0 RBER is very tough shifting the read offsets. So there is very low margin between 2 adjacent states. But in case of TCFlash 2 operand, L6 state doesn't exist because we have programmed with the LSB, with MSB and CSB page with the same data. So if we shift it, we have still a wide margin where we can just shift more. So if you check the layer dependencies of NAND flash of TCFlash, we will see that for AND or an XOR operation, we get 0 RBER. But for the other operation, we see more errors, and we see that the lower deck of 3D stack are found more error prone. We also evaluated our performance with an image segmentation workload, and what we see that TCFlash 3 operand operation achieves 25% faster than Parabit and over 100x faster than in-storage computing, which is Cosmos implemented in OpenSSD. Finally, our key contributions are we have demonstrated the first commercial off-the-shelf chips implementation of in-flash processing. We have only used our user mode commands and achieves 0 raw bit error for 2 operand bitwise operation. And in our future work, we want to evaluate the performance across different workloads. We want to scale our scheme for QLC and PLC NAND flash memory, and we want to extend the support for different encodings. Thank you all.